Alright, so this is going to be a little bit of a longer video, but we're going to cover a lot of really cool topics here. Questions came up a few times regarding sightlines within Revit and how to calculate them. We used to do it with families, we used to do it with all sorts of other things, but you generally have to be fairly manual with that. Then Dynamo came along and we started to use things like ray bounce. There's a really great blog post on the Revit Beyond BIM blog that I'll link below that shows the ray bounce method, where you literally shoot beams of light basically out from an object and you can calculate what's going on, what the sight lines are. And that's one method I used to use actually as well. These days, there's a few more packages that help us with this, so we're going to look at an option in the Space Analysis Toolkit, which primarily focuses on generative design. That being said, we can use it for whatever the heck we want, so that's what we're going to do today. In this case, I'm in Revit 22. This should work back to Revit 20 or 19 even, I think. So you'll just have to try. The main thing is Dynamo 2.x. You need a 2.0 and up version for this, so that is one thing to keep in mind. So what we're going to do is go ahead and fire up Dynamo. I have the complete graph saved as well. It's linked below if you just want the graph, but I encourage you to check out the tutorial because you'll be able to build it from scratch and be able to just build this whole concept out for yourself. So let's go and click New to start a new blank workspace. So the first thing we're going to do is we're going to build this to work with rooms. So I guess to kind of evaluate what we're going to build, let's look at the graph as it is. So this graph will actually take our rooms from an active view and build them out with the door openings carved out. So the Space Analysis Toolkit takes boundaries, which are lines, and it uses those to calculate the obstructions for the sight lines. So that's what we're doing here. This part is the part that we'll go through first. And then the other portion would be actually calculating the view cone based on an object. And in my case, I'll use an entourage because it's kind of cool to be able to see that person in here and see their sight line. So this is what we're going to be building. All right, so back in our blank graph, the first thing we need to do is we need to retrieve the active view. So if we search for active view in our library, there are a few options in here. There's one out of the box. This node is okay, but not great because it takes a document input. So I tend to not use that. I like to use the Spring Nodes package for this. So that is a custom package called Spring Nodes that will automatically just get the view you're in. And then you can put a Boolean in to toggle it to refresh it. In addition to this, we want to get the rooms in the view. I don't want to get all the rooms in the entire project. I want to be fairly specific with how I'm working. So once again, Spring Nodes has a really great node for this, and we'll navigate to it manually. If we go to Springs, Revit, there should be a selection category in here, or collection. So we'll go to collect, and we're going to do elements and view. So Spring Nodes also has some really great nodes for collecting things, and this is a perfect use case for this. We're not going to hook this up quite yet because if we leave category blank, it collects everything in the view, literally everything. So what we'll do is we'll just use a categories node for this. And we'll assign that category as rooms. So if we hover and pin, we'll see that the node hasn't ran yet, and that's because I haven't fed in a view. So let's go ahead and plug a view in, and we'll notice that we have 31 rooms in this view. So it's really nice. This works with multiple views as well. So this collector is pretty stable in that kind of thought concept as well, to where we can just use it to collect a whole bunch of different things. I really like to use this node. It's my go-to pretty much always for these kind of actions. As you can see, this node does collect them as a nested list. That's not really something I want in this case because I am focusing on a current view. So I am going to go ahead and flatten this thing. And I have a tendency of unpinning previous ones as I work. Once again, I mentioned this in pretty much all the videos lately, but if you see these cleanup tools, these are in Monocle, and it just lets you annotate and group and align all your nodes really well. So You can use that, or you can just not align your nodes. I encourage you to download Monocle to be able to align all those nodes. Awesome. So as we're working, we are going to practice some clean code and group all of this, just because even though this is a tutorial on how to build out this graph, I don't want anyone to get lazy with their grouping or annotating their code. So we're just going to go ahead and do that as we work. So we'll select all of the nodes, and I tend to use this purple group for things that are inputs, and we'll say collect all the rooms in the active view. Awesome. So now we have all of our rooms collected really quickly. We'll go ahead and hit save. And then I'll name this view cone working. Awesome. So now we have that graph saved for us to be able to not lose our work. All right. So another consideration, and I'll make another video on this, is if you're working with rooms, you're going to want to filter out rooms that are unplaced rooms. In my case, I'm in the advanced sample model, so I know all these rooms are placed in this view. So that's not something we have to consider right now, but generally speaking, we will want to filter out rooms that are not placed, and we do that by the area parameter. So I'll make a video on that and link it as well. Awesome. So now what we want to do is we want to get the boundaries of this of these rooms. In Revit 21 and up, there is a really awesome, I think it's Revit 20 and up, there's really awesome nodes in the Revit Elements room category. We navigate to that, we will notice that we have a few different options in here. We have things like center boundary, core center, and finish. In our case, we just want to calculate those sight lines from where a person would be standing, so we want to use the finish boundary, which would be that inner boundary of the rooms. We'll go ahead and connect this flatten node into the finish boundary, and we'll observe what it did. So as you can see, it obtained all of those room boundaries very, very quickly for us. What's interesting is the finish boundary is available even if you are calculating rooms by centerline or something. So this is always available in the API, which is really cool. Another thing worth noting is the first list is the outermost boundary, and the subsequent list are all of the inner boundaries. So in the case of working with this, we want to make sure we remove doors from the outer boundary. So we'll look at how to do that next. And I can kind of illustrate this by hiding the preview. You don't have to do that if you're following along. So what we'll do is we'll go ahead and get the first room just to demonstrate this point. This is my first room. And I'll go ahead and hide this. Once again, you don't have to follow this part, but I think it's worth noting. We can separate the first thing out from the rest. So if I hide this preview and I just preview the outer boundary, we can see it's that outer rectangle, and the inner are all the little column cutouts. So that's the logic that we want to use for this. So in our case, we are going to go ahead and use a deconstruct on the finish boundary node. This is kind of interesting because if we just use it how I have it right now, it's going to deconstruct the list on all of the rooms as a whole. So it's not deconstructing each room, it's just separating out our list, our first room, from the rest. The way we work around this, and we won't get into this concept a whole lot on this video, is we need to work within the sub list. So in the case of these rooms, and I'll hover and pin, we are currently working at this at L4. So we are working out here. That's why we're getting that first room and then all the rest of the rooms after. We want to actually work a little bit deeper into the list at L3, that we were working on each room individually. So the way we do that is we click on use levels and we switch it to at L3. And as you can see, my background preview updated and all of the outer lines are on that first output list. Little difficult to grasp, but I assure you, just mess with deconstruct, just kind of get a feel for it. It is a node that's really useful, but this outer perimeter is going to really help us here in a little bit. Awesome. So now what we need to do is we want to create joined curves from our outer curves. So if we were to navigate into our geometry category we can go to curves, and I want to create a joined curve or a polycurve. We have a node in here called by joined curves. So this is really nice because once I connect this node, it creates single curves for each room. So this is really nice when I want to work with the outer perimeter because I'm now able to just work with one polycurve instead of several subcurves, individual curves. The join tolerance, we can leave that blank. It has a default value. Older versions of Dynamo might not have the join tolerance parameter, but they do have the by joined curves node, so keep that in mind. Awesome. So now what we could do is we will group this. We aren't going to use this quite yet, but this will be for our door calculations. So what we'll go ahead and do is we'll say get room outer boundary for door calculations, because I want to trim the entry doors for each room from those outer curves. So now we can go ahead and hit save, and this is kind of staged and ready to go. So this is what we have so far. So I'll leave that there for a second, just so that way we kind of see where we're at. Once again, I disable the preview of previous nodes as I'm working, so always keep that in mind. Awesome, so I did say that I want to work with the doors within the rooms. So if we search for doors in the library, a lot of times we'll kind of get a hint at what we're looking for. There are a few different nodes in here. If we hover on the first one, this will require a package called Clockwork. So Clockwork, Spring nodes, those are packages to have installed for this. You go to packages, search for a package to install them. Essentially, Clockwork and Spring nodes you should have installed anyway, so always keep that in mind. If we hover on this node, it says retrieves all doors that are associated with a room, hosted in walls or roof. And I think it gets windows even, or there's another one for windows. So we'll place this node from Clockwork, and we'll start looking at what to provide it. All right, so it takes a room input, and then phase in Revit 21 and up is italicized. That means that it's a optional input. So what we'll do is we'll go ahead and fulfill the room input and observe what's happening. So now we have a grouping of doors per room. So really quickly we were able to retrieve that information. This is where custom packages really shine, is they add functionality, the package authors, that they want, and we all get to use it, which is really awesome. So now what we're going to do is every element in Revit has an object assigned to it called a bounding box. I want to trim the doors out from these curves, so I'm going to just use a bounding box. If I were to get the geometry of the doors, that could be a very heavy process, and I just want the overall bounding of the thing. So that's what we're going to do. If we navigate to Revit, navigate to Elements, and then Element Singular, we will see all of the shared criteria between elements within Revit. In this case, we know that we want to query the element for something, so we'll scroll down to the question mark category, and we'll pick bounding box. So like I said, every element has a bounding box within it in Revit. So we'll go ahead and connect the doors to the element, and we're going to get an error, but that's okay. We'll clean up our node a little. We're getting an error because one of the curtain wall doors is a little weird, and we can see that with this null value in here, these null values. There's not really a way to work around that, so we're going to approximate some of these doors. That's kind of where I was going when I say that if you get the geometry of every object, it might fail or be very heavy. That's part of the reason why. The easiest way to clean up these null values is to just clean the list. So if we do list.clean, this will actually take an input list and a boolean, and I'll use a code block for this. So you just double click for a code block and type false, and it will clean out those null values. The package Lunchbox used to have a node called remove nulls, but this list clean is out of the box and it just works. That way you don't have to rely on a custom package for that list interaction. Cool, so now we have the bounding boxes getting collected. The additional step here, so bounding boxes, just like Revit elements, have their own parameters to them as well. A bounding box is an abstract geometry. So if we navigate to extract, abstract, bounding box, we can see that it has its own values that we can use as well. In addition to creating them from geometry, we are able to convert with this little lightning bolt category to a cuboid. So let's go ahead and place that node and connect our bounding boxes to our cuboids. So now you can see that we have all of our door locations visualized as boxes. This is really nice because that gives us a great object to trim out of the perimeter boundaries of those rooms. So we'll go ahead and leave that preview on for right now just because I want to keep seeing them, but we're going to hide it eventually. And since this is kind of like a pretty controlled interaction, I'm going to go ahead and group this as a green control group and explain to the next user what I was doing, or to myself if I open this at a later time. And once again, the completed graph has all these groupings and notes for you. I just named that get door bounding boxes to trim from room boundaries. A lot of times if I have a node that causes errors or has errors that are ignorable, I'll add a note. So if you hit Control W on your keyboard, you can add a note object into your Dynamo canvas. And I'll actually type this note out and say, errors right here are ignorable. And there are ways to suppress these errors, but a lot of times it's just not worth going through it. I'll just add a note letting the user know what's going on. We'll go ahead and save. And now we have our doors converted to bounding boxes. Awesome. So this is what we have so far. This is kind of where we are. This is that step 3, I guess, of the process. So what we need to do now is we want to remove the doors from the room element. There are ways to trim curves directly with these solids, but it gets a little odd. So I tend to like to work with the room solids as well. So once again, if we navigate to the Revit category, elements, and element singular, we have all the options available to us for elements. Within the little action category, we can extract the geometry from an element. That's not the one we want. We do actually want to get the solids of the element. So we'll scroll down, and in the query category, we can get the solid. Geometry works too, but it will retrieve more than we want. It will retrieve things like curves and things like that. So we want the element solids node. We'll plug this in. Dynamo will probably think for a second with this, but now we have all of the solids of our rooms and all the solids of our doors. So really quickly we got those, and you'll notice that these are nested lists, and that's because sometimes an object can have multiple solids. In order to work around this with rooms, we'll just combine those solids. Just like the bounding box, solids have their own parameters available to us. If we navigate to geometry, solids, solid, there are a few options available to us. Under this action category with the plus sign, we have a by union option. We'll go ahead and plug this in, and we'll see that we have a flat list of solids now. Once again, I'll hide the previous iteration so that way I don't have overlapping geometry. And now we have all of the room solids available to us. So now another cool thing with these single solids is we are able to cut out these door openings within here. So we are still in the solid category within the library. If we navigate down, there are a few action parameters in here as well, to where we are able to subtract and things like that. In our case, a door can have multiple, or a room can have multiple doors. So we do want to remove all of those door openings. So we are going to use difference all in this case. It takes an individual solid and then a grouping of other solids. So now you'll see that it ran. We'll hit save, and something happened. In order to visualize what happened properly, we're going to right click and hide the bounding box to cuboid. That was the door cuboid. And we'll click on the difference all, and we'll kind of navigate around. I'm holding down escape on my mouse and just using my right click to navigate. So as you can see, we have little notches on each of the rooms for the door that is inside of it. Pretty cool. If we were to toggle back on the overall solid geometry, we will see that they don't have those notches. So we've just trimmed out those doors from our rooms, which is pretty nice. It's not easy to do otherwise. So we're using Dynamo nodes to do some pretty cool things. And I might bundle this interaction as a Dynamo node within Rhythm. but it is worth knowing all the concepts, and I thought that it would make for a really cool tutorial. So we're going to clean up this group as well. We'll group it. We'll go ahead and make this probably an orange, which I like to use for actions. It says to Revit, but I tend to like to use it for something that's doing an actionable thing. And we'll say trim doors from solid. That way we know what this is doing now. And we'll hit save. Awesome. So now that we have our polycurves down here and our rooms with the trimmed doors, we want to get the polycurves that work for that perimeter. And I'll zoom out just to show where we're at now. We have a total of 4 groups, which really isn't that bad, considering what we've done so far. So now what we're going to do is we want to figure out what curves intersect with our room solid that we now defined. In our case, I'll go ahead and navigate to the geometry category. There are some actions right in here as well. So this modifiers category has actions that are shared between all geometry. And there's one in here called intersect. So if we hover, it says get the intersection geometry for this object and another. So this is really nice because we can go ahead and place this node and use it on geometries. Polycurve is a geometry and a solid is a geometry. Once again, we do have one polycurve to one room solid. So it's a 1-to-1 match and each list has 31 items. Awesome. So now that we have that, we need to hide some preview geometry just to see what's going on. In our case, we're going to hide the difference all, and we're going to hide the original polycurves. Once we do this, we'll hit save. We can hold down escape to navigate our background and see what's going on. We now have all of our rooms with the doors cut out, so that way we can use those. So it's really nice. We can start to evaluate this. There are some instances where we could trim them out of other curves or make those bounding boxes bigger or something. You can elaborate on that a bit more. Generally speaking, this is a good start though. So now we have those available to us as the intersect. So these would be our boundaries for space analysis, which we'll get to here in a moment. Another thing that we need to consider, so if we look at all of this, these are lines. All of them are lines. Some of them are arcs. On the inner curves of the rooms, some of them are arcs as well because of those columns. So we need to rebuild these things as lines. This is where it gets a little bit weird because the space analysis package does require straight lines, but we'll work through it. So this is another section of this. What we need to do is we need to combine the inner boundaries with the outer boundaries. So the way that we do that in Dynamo is we can type in list create and get a list create node that we can add plus signs to for inputs. And we're actually going to take this rest output down here and plug that in, and then the intersected room boundaries. And now you can see that we have a whole list of curves at this point. I'm going to go ahead and disable the preview on that previous node since we have them combined now. So the way I like to do this is since space analysis actually doesn't care at all the list structure, I'm just going to flatten this completely out. So we'll place a flatten node, plug that in, and we have 387 boundaries. Once again, we'll disable the preview of our previous node just to keep it clean. Within Revit, it's really easy to reconstruct curves as lines and things like that. You just kind of have to think it through. In our case, we have a list of curves at this point. So if we were to navigate to the curves category and the curve subcategory, there are a few options to us in here. I do know that I want to create a bunch of points to make some clean lines on. So I tend to use point at parameter for this. A parameter is any value from 0 to 1 on a curve that would result in a point. So each curve has values from 0 to 1 and an infinite amount of numbers within those endpoints. So we'll place this node, we'll hook it in, and we'll instantly get the parameter 0 at every curve. So that's the start point in this case. In my case, I'm going to use a code block for this. We need to generate a list of values from 0 to 1. So this is called a range. The easiest way to do this is a code block, and you can pick how dense you want it. So how clean do you want these curves to be? So in my case, I'm going to do 0 dot dot 1 dot dot number 10. And what this means, I'll zoom in, is start at 0, end at 1, and give me 10 points within that. We'll plug this in, and we'll see that it didn't quite work yet. I don't see a bunch of points on my screen. That's because by default, Dynamo is giving us points on just that first line because it's doing a 1-to-1 match. In order to make this work for all of the curves, we need to right click, go to lacing, and change it to cross product. What this means is we're telling the node work on everything that I'm feeding. So give me all iterations. It's literally like just looping through it all. I'll try to link to some videos explaining lacing. There are some examples in the primer for this. So now we can see that we have a whole bunch of points, 3,870 versus 10. So really quickly we've went through and done a whole lot of points. We'll go ahead and hit save. You'll notice that it's updating live, and that's because I am staying in run automatic for this. You can go to run manual if you want, but generally this workflow is not too heavy. It seems kind of heavy, but in the sample model it's running pretty quickly. Cool. So now that we have those reconstructed as points, we'll hide the previous geometry and we'll just see points. In our case, we want to generate another polycurve because a polycurve is just a curve made up of lines. So if we search for polycurve, there should be an option in here. In my case, it's option 4 to create them by points. So we'll place this node. By default, connect first to last is false. That's fine. We don't really care because we know that all of our points do connect, and we'll plug our points in. So now we have another list of polycurves. In this case, we have 387. So we took all of those and we combined them into polycurves. We can go ahead and hide the point geometry, and we'll see that it looks pretty much the same, but if we zoom in, you will see some segmentation on the circles. So that's good. That's what we want. We'll clean this up a little bit. And once again, this connect last to first has a default value of false, and we'll leave it alone. So with polycurves, we do have parameters available to us. So if we navigate to polycurves in the library, we do have the option to get the underlying curves from it. So polycurve.curves, if we connect this, it breaks it down into the 10 or the 9 curves that comprise it. So that's really nice because now we have lines of every one of those objects. So we'll go ahead and hide the previous iteration, zoom out, and we now have our lines. Once again, I'll go ahead and flatten this because space analysis doesn't care if it's a flat list or not. We'll plug that in and hide that previous geometry. So that's one of the bigger topics of this, is reconstructing those curves as lines, but I think it is very valid, and once we break it down, it's not too hard to understand. So now what we can do is we can go ahead and group this. We'll group this first part as a green group, and we'll say get curves without doors, because that's what this was doing. And then the second part is reconstruct as simple lines. And we'll put required for space analysis. Awesome. And we'll go ahead and hit save. And now we have all those reconstructed curves. So another thing that we're going to want, we'll go ahead and build this before we do the space analysis, is we want to be able to select an object. In my case, I placed an entourage because I know that it's a point-based element, and we can rotate it to get the facing direction of it. So it's really kind of a cool object to use for numerous reasons. So what we'll do is we'll place a RPC. So I'll go to component, CM on my keyboard, and we can see that this one's pre-selected. And we'll go ahead and hit spacebar to paste it somewhere. I don't know if you know this, but if you hit spacebar while on like a door object, it will kind of follow that, which is kind of cool. So as you're trying to place it, it's kind of matched to that arc right now. So kind of a cool little thing. And you just hit spacebar while hovering. So I'll try to make it face the door actually. And now it's facing the door. So that's another little Revit tip snuck in there. So we have that placed now. In my case, I want to select that entourage. So let's go ahead. We'll make Dynamo bigger real quick. and we'll right click and search for select model element. So this node's great because it lets you pick any model element. We'll hit select, drag Dynamo out of the way, and make sure you pick your entourage. And now we have this entourage selected. It gives you the name of the instance, so apparently I used one called Florence, so there we go. What we can do is, once again, elements all have properties. We're going to search for these just to make it easy. We're going to get the location of this entourage. We'll plug that in, and we can see the location back there in the corner. We want to get the facing orientation of it. That way we know which way to look within the toolkit. So if we navigate to Revit, Elements, Family Instance, we see that it has a few additional options beyond element. In our case, we do have one under the query called Facing Orientation. So this is really nice. I've used this for curtain panels as well, just to see which way they're facing. So it gives you a vector pointing the direction that it's looking. Just for fun, we're going to go ahead and do element.geometry. So we'll search for that node, element geometry, I think. Sometimes the search is a little fidgety. That way we can see what we selected. So it's a little preview of the entourage, and it shows the pointing direction too, which is kind of nice. So that's why entourage is also cool to use, because it's something that's recognizable pretty easily. We'll go ahead and group this as a purple group for input, and we'll say select entourage. You can use whatever element you want. You could see what sightlines a toilet has if you want, and get the location data for it. Awesome. So now as we select these objects, we can visualize them, except for the vector, but the geometry we can as well. We'll go ahead and hit save, and we'll zoom out just to see where we're at. This is all the stuff for the room data, and this portion at the bottom is for our entourage. So that's going to kind of sit there and wait for us to finish out some stuff with space analysis real quick. So once again, space analysis is a custom package for Dynamo. It was developed with generative design in mind, but we can use it for pretty much whatever we want, and it's a really fast package. It runs quickly given what it does. It has pathfinding and all sorts of stuff. I encourage you to check out the Dynamo primer and the Dynamo blog, which has examples on it. If we navigate, it does have a few different categories. One of the most confusing concepts of space analysis is the idea of a space lattice. It's a very weird name for something that means analysis grid. It's just an area that we want to perform these analysis on, like sight lines or sound attenuation or anything like that. So it has a whole lot of different options. Like I said, it has pathfinding too, which is pretty cool. If we navigate to Core Space Lattice, we see that we have a few options here. So this is a little confusing if you don't know how to build it out, but we're going to go through it and try to demystify it some. So we'll place the by bounding box and lines node, and I just know it's going to go over here by my curves that I constructed for it, so we'll drag it over there, and we're going to primarily be in this area of the graph for a few minutes. So let's navigate over here. So you should see your flatten and your polycurve curves if you're following along. In our case, we know that it takes a list of lines as barriers, which we constructed here on our flatten, and it takes a bounding box for the entire lattice that we want to build. It also takes a resolution, which is a really low number by default, so we're going to have to bump that up, or else Dynamo could crash because we're trying to do too tight of a resolution. In our case, we want to construct a bounding box that represents the whole analysis area. The easiest way to do this is to go to Geometry, Abstract, Bounding Box, and this little plus sign category for Create has a by geometry option. So it's really nice because we were working with bounding boxes from Elements earlier, but we can also work with them from Dynamo geometry. So we'll go ahead and plug in our geometry, and now we have a bounding box. Once again, bounding boxes are abstract. They're kind of weird, so they don't have a 3D preview, so we don't have to disable this in this case. If we were to convert it to a cuboid, you would see the overall bounding box of the entire area. So kind of cool, something to keep in mind. That will be our bounding box input, and we're going to double click for a code block and type in 300 for a resolution. If you're on the sample model, which is in metric, that's a pretty good resolution for it to run quickly, and I just know that from trial and error. The last input is the barriers input, which is a list of lines that we constructed earlier. So now we'll see that we've constructed a space lattice and a total of 3 nodes. So not as scary as it seems, it's just a weird concept to get used to. So we'll go ahead and group this. We'll do an orange action because we're creating something. And we'll say build the space lattice. And we'll hit save. So now we have that to work with. We don't have to disable any geometry now because space lattice doesn't show any unless you ask it to. Awesome, so within the space analysis package, we have a few other options in here. If we scroll to visibility, we have a view field or a view cone. In my case, I want to match a sightline of a person, which is typically about 130 degrees or so. You can make that whatever you want. If you have security cameras that have a wider field of view, you can put that in as well. There's a lot of options here. So I know that I want to use a view cone. There's only one node in this category, so we'll place it. If we observe the inputs, we see that it takes a viewpoint, so where to view from, a direction, which is a vector, which funny enough we already have, which is pretty cool. And then it takes some other parameters like width of the view and how far out you want to shoot and things like that. We'll leave it default for now, but we're going to change that. In this case, if I scroll out, I know, and let's move our entourage group over here by the area that we're actually working in. I know that I want to view from where my entourage is located. I want to look the same direction as my entourage. So now we fulfilled those inputs for the view cone. So as you can see, nothing's happened in the background. A bit of a bummer. So we just need to actually visualize these results. If we look at this view field category within the space analysis toolkit, so we actually want to place the one by space lattice and view cone. As you can see, if you hover over the description, it does say that it computes a field of view paths from a single view cone. One of the inputs is a space lattice that we created up here on this orange group, and the other input is a view cone that we created right here from our entourage. So now as you see, we have a view field object type created for us. Once again, we don't see anything quite yet, and that's because we have nothing visible. In space analysis, there's another category called visibility grid. There are a few options in here where you can create different ways. We just created a view field, so I know that we want a visibility grid by view field. Oftentimes the node name should give you a little bit of a description as to what it wants. We'll connect view field to view field, and now we have a visibility grid. So we've created a few different object types. We've created a space lattice, which is the underlying geometry, a view cone, which is what we want to analyze, and a view field that is the raw results. And then we've gotten a visibility grid, which is a visualization of the results. So quite a few topics right in there. So now what we can do is we have that visibility grid constructed. We can't see anything yet, but if we look in the space analysis category for visibility grid, we see that there are some action parameters in here. We have points, surface, value at point, and values. This is really cool because the visibility grid already has a surface for us. So we'll place that node and connect it, and we'll see that we now have a surface that we can use to visualize. If you're in the sample model, you're going to get this warning. This warning says that you need to consider using a bigger working range. If you go to the settings menu, in versions of Dynamo that have the settings menu, you can go to the geometry working range. If you're in newer versions, you can go to preferences and geometry scaling and change it to large. So that's where that is. I'll show where that is on the other version here in a second as well. Once I do that, it will start running and that yellow warning will go away. And that's just because Dynamo has some protections in there for how much geometry it shows. So we just need to work around it. In older versions of Dynamo, that settings menu is under settings and geometry scaling. And then you pick large. So that's how that interaction would look in versions older than 2.12. All right, so now we have a surface. We want to color that surface based on our values. And we'll do some grouping here right now as well. So let's go ahead. We'll put these all kind of together like this. just because they all go together. And we'll say generate a visibility grid. So there we go, visibility grid, really quick, awesome. And we have the underlying surface. Inside of the visibility grid category in space analysis, we also have values. So this creates a range of values from 0 to 1, which it says on here if you hover. 0 is completely invisible and 1 is completely visible. So that's really cool because 0 to 1 are values we can use for a lot of things. So we'll go ahead and get those values and we'll see them here. So what's nice about these values is we can actually use those to generate color ranges. So if we navigate to display, color range, we have a few options available to us. I like to use the color range node because it has some default colors for us by right away, which is really nice. So I always like to use this one. We'll define some custom colors here in a second. But what we'll do is we'll just plug the doubles right into the value. So the value input wants values between 0 and 1. The visibility grid values gives us values from 0 to 1. And what it does is it retrieves a color along this range that matches those values. So 0 would be the left, 1 would be the right. Really quickly, we are able to start looking at visualizing things. So in the library, we now need to navigate to, we're actually just going to search it. Within surfaces in Dynamo, we can actually put colors on the surface to visualize them. It hasn't been around forever, but it's been around for a while. So if we look for by surface colors, we actually have a really cool option in here to take a surface and a list of colors to color a surface. This is the fastest way to do this right in Dynamo. As you can see, it has an input of colors, which it already gives us a few. We'll plug the colors in and we'll plug our surface in. Right now it doesn't look like much, and that's because our original surface is hiding the colored surface. So what we need to do is right click on our surface and disable the preview. And now as you can see, we have a visibility grid that's being visualized. At this point, you're at a point to where if you were to minimize Dynamo or drag it to the side and move your entourage, it will update on the fly. So that's really cool. This is a point where you already have something going on. Right now it's giving us visibility or sight lines 360 degrees around our object, so we'll fix that next. In order to clean this up, let's go ahead and group these things. So we'll kind of drag them around and group them, and we'll make it a green category for this, and we'll say this visualizes the results. So now it's really good. We'll hit save. We want to change that sightline to more of a true view cone, and that's done in the angular width parameter for the view cone creator. So the simplest way is double click for a code block, and we're going to type 130, which is a typical view field, I think, for a person. And then we'll plug that in. And as you can see now, wherever this entourage is facing, it's 130 degrees from that. Let's see. Let's change where mine's looking. We'll move it into the hallway. And yeah, there we go. So now you can see she's facing that way, and we kind of see how that's working. So let's rotate this thing real quick. That way it's facing the other way. And let's drag it around. Cool. So you can kind of see how that's working too. To where it is updating on the fly. What's really cool is we are getting those columns of obstructions. So you can add more obstructions if you want to this workflow as well. The colors are a little confusing right now because blue is completely in sight and yellow is not. So let's fix that real quick. In Dynamo 2.1 and up, I believe, there is a node called Color Palette, which lets us use this cool color dropdown to create those values. So we're going to do from black to yellow, black being you can't see it and yellow you can. We'll combine these, and in my case, we'll just use this monocle combine node. So if you have monocle installed, this auto combines things for you. And we'll plug this into our colors input, and you can see our color range updated. So we'll put these in this grouping up here, kind of clean it up, cross window and add to group. And now we have from black to yellow. The background didn't update, and that's because the indices isn't fulfilled yet. This node's weird because it doesn't warn you. So if we double click for a code block and do 0.1 just to get a 0 and a 1, we can plug this into the indices and we now have that ability to visualize that. So that's kind of a weird thing. It's something to keep in mind with the color range node. And funny enough, black's way too dark, so let's make a gray or something. That way it's a little clearer. And now we have that getting visualized. So if we were to zoom out, this is the entire graph. It's not enormous, it just has a lot of concepts in it. I'll add chapters to this video so that we can navigate through. But we are now building that surface based on that entourage looking from a direction. So in the case of Revit and Dynamo, I will tend to kind of shrink Dynamo down a little maybe and zoom out. We'll collapse the library too. That way we can see it. And then I have Revit over here on the right. If you're working on two screens, this is way easier. And what we'll do is we can move this entourage around now. So I moved her way down here in the corner, and you can see that she sees down those two halls. If you're in the vestibule, that's what you're seeing currently. And there are some room boundaries in here, so they are obstructing some of them, so we'd have to filter those out probably. But as you, quote, walk around the building, you can see kind of where they're seeing. So this entourage is able to see right into that room a little and down the hallway. So in the case of rotating this, we'll kind of, and every now and then it'll give you more sightlines than what you're really asking for. It's kind of interesting. But that's how it's seeing inside that room. And that's how it's seeing inside the room once again. So you can kind of start to evaluate this. In this case, I'm missing the stairs as well. So that's probably something I would add later as an obstruction. But as you navigate, you're able to see this thing really quickly update. You could also add multiple views. So if you have, like, let's say cameras, you can actually create a view field. So if we navigate to the space analysis package, you can actually create or a visibility grid by intersecting several view fields. So you can combine several cones and see what kind of overlap you have. You can do things like for scanning, laser scanning, what your view fields are. And this is much faster than the ray bounce method that we've used previously because it's all running on that custom package. So yeah, this is kind of what the overall view would be because right now it defaulted to 360 for some reason. But yeah, there it is. Let's kind of zoom out and take a look at the entire graph. We have something like 8 groups or something to create something really cool. If you wanted to evaluate other levels, you could and just refresh your view input, or you can use this in Dynamo Player perhaps or something like that. But it's kind of nice to get the interaction live within Dynamo and Revit. So there it is. If you stuck around, I hope it helped out. A lot of topics in there. And yeah, have fun with it, and thanks for checking it out.